Section 11.3.15-T. A researcher wanted to determine if carpeted rooms contain more bacteria than uncarpeted rooms. The table shows the results for the number of bacteria per cubic foot for both types of rooms. So here's the first part, carpeted, and then here's the uncarpeted. Alright, so what we want to do is we want to be able to test the statement that carpeted rooms have more bacteria than uncarpeted rooms at the significant level of 0.05. The normal probability plots indicate that the data are approximately normal, and the box plots indicate that there are no outliers. So let's go ahead and just verify that on StatCrunch. So I'm going to take my information here. Okay, here's my data, and I'm going to open it up in StatCrunch. Okay, now that I've opened this up in StatCrunch, I'm going to go ahead and graph this. So first, let's graph the normal probability plots. So we're going to go ahead and go to graph. We're going to go to the QQ plot. We're going to do carpeted. And then let's go ahead and just select compute with the correlation statistic. Okay, and the normal quantiles are on the y-axis. So here, we're going to go ahead and plot, and we can see here that this is forming a line that represents a normal distribution, and that's for the carpeted. Okay, now let's go ahead and now graph the other one here. So let's graph the QQ plot for the uncarpeted, with the correlation statistic and the normal quantiles on the y-axis. When we do that, we can see that we also get another correlation coefficient of 0.9, and we can see that both of these contain a normal probability distribution. Okay, now let's go ahead and check out the box plots. So we're going to go ahead and graph. We're going to go ahead and select box plots. Go ahead and do the carpeting. We're going to draw the boxes horizontally. Okay, and let's go ahead and compute, and we can see that there are no outliers in this box plot. And then likewise, let's go back down and select box plot again. We're going to do the uncarpeted, draw the boxes horizontally, compute, and we can see here that this also does not contain any outliers. So that tells us and proves to us the fact that we can now say that the hypothesis is going to be able to now follow the guidelines. So to test the hypothesis regarding two population means obtained from independent samples, we just follow the steps, meaning that the two independent samples are obtained by simple random sampling, or the data result from a completely randomized experiment with two treatments. That is true. The sample data come from a normally distributed population with no outliers, or the sample sizes are large. Well, we found out from the first part by looking at the graphs. And then for each sample, the sample size is no more than 5% of the population. So that means here we have 1, 2, 3, 4, 5, 6, 7, 8. So if we take n, we're going to we want to make sure it's going to be less than or equal to 0.05 of the population. Well, we can say that 8, okay, is going to be less than 0.5 or 5% of the population. Now, to determine the null and the alternative hypothesis, the hypotheses are structured in three ways. Two-tailed is equal, not equal. Left-tailed is equal, less than. And right-tailed is equal and greater than, where you have population mean 1 is equal to population mean 2 for the null. Now, if we let population 1 be the carpeted rooms and population 2 be uncarpeted rooms. So the first thing we want to do is we want to be able to then determine, okay, what is the null and what is the alternative hypothesis. Okay, well, we know that population 1 is going to have population mean 1, and we know it's going to equal population mean 2. Okay, and now we know that the alternative hypothesis is going to have the claim. Okay, well, let's go back and talk about what the claim is asking us. Okay, it's saying the researcher wants to determine if the carpeted rooms contain more bacteria than uncarpeted rooms. So that means if it says more, then we're looking for greater than. So here, this is going to be population mean 1 is going to be greater than population mean 2. Okay, step number 2. We know that it's greater than, so that tells us that we're going to have a right tail. And in the problem, okay, it doesn't give us the significance level. And if it doesn't, then you always choose a 0.05 level of significance. So therefore, in this particular problem, alpha is going to equal 0.05. Okay, now the next step is we want to be able to now to determine the test statistic. So here is the formula for the test statistic. So that means we need to find the mean of population 1, which is the carpeted rooms. And then we also got to find the mean of population 2. Okay, and then we also need to find the standard deviation of population 1 and the standard deviation of population 2. Okay, and then we also need to determine, okay, if we want to find mu1 minus mu2, okay, well, what do we know? Well, if we look at our null hypothesis, okay, and so this is what we're looking for, mu1 minus mu2, and I'm going to write that down here so we know what that's going to equal. If you take a look here, we can see that mu1 is equal to mu2, so I'm going to write that here. So mu1 is equal to mu2. Now, if we want to let this equal to 0, we're going to subtract population mean 2 to the left side, and what's left is 0. So that tells us that that is going to equal 0. Okay, now that we found that, we want to be able to plug this into our formula. Before we do that, we need to find the mean and the standard deviation. So in order to do that, we're going to go back to StatCrunch. Okay, so let's go back to StatCrunch. Okay, and we're going to go to Stat and then Summary Stats, and then we're going to select columns. So we want the carpeted, we want the uncarpeted. Okay, and then we have n, sample size, the mean, and the standard deviation. So let's go ahead and select compute. Okay, so from this information, we're going to be able to determine, okay, what is the mean for the carpeted? We can see that the mean is 11.4. We also know that the mean for the uncarpeted is 8.925. Okay, and the standard deviation for population 1, we're going to round that to 3 decimal places. So that's going to give us 3.585. And standard deviation for population 2, round it to 3 decimal places, is going to be 3.418. Okay, so now what we do is we have all our information, okay, because we also know that population size 1 is 8, and then the population sample size is 8 for the second one. So let's go ahead and find the test statistic. So we know that mean 1 is 11.4, and we're going to subtract the population mean 2, which is 8.925. And that's going to be minus mu1 minus mu2, we know is going to be 0. Okay, and then in a denominator, we have the following. We have the standard deviation of population 1, which is 3.585. We're going to square that and then divide that by population 1, which is 8. And then plus, same thing here, standard deviation for population 2 is 3.418. We're going to square that and then divide that by 8 as well. Okay, so now let's go ahead and put this in our calculator so that we can figure out, okay, this test statistic. So in the numerator, we have 11.4 minus 8.925. Okay, and it's minus 0, so we don't need to subtract that, so this is what's in the numerator. So once we have the numerator, we can go ahead and just hit divide, so we can divide the answer by the following. So we're going to select second square root, okay, and so what we're going to do is we're going to put parentheses around this first one, and then parentheses around the second one. So we don't mess any of the order of operations. So we have the square root, we have parenthesis and second parentheses, so parenthesis, and then second parenthesis, 3.585, okay, close the parentheses and square that, and then divide that by 8, and then close the parentheses. So that's the first part. Then we're going to put in plus. Then parentheses, second parenthesis for the numerator, 3.418 with the closed parenthesis and square that. And then we're going to also divide that by 8 and then close the parenthesis to close that part. Hit the arrow key to the right so we can go ahead and select enter, and then we get the following test statistic. So let's go ahead and copy this answer. So this is our result, and if we round it to 2 decimal places, we get 1.41. Okay, now that we have the test statistic, now we can go ahead and then draw our bell curve. Okay, so we want to draw our bell curve so we can see what we're looking at here. So we have our bell curve. We know that our mean is going to be 0, and we have our test statistic located at 1.41. And we want to find the value to the right of that because it's greater than. We want to be able to find the p-value. Okay, now if we use the table, the t-distribution, it's not going to give us an exact p-value. So we can use another calculator function that we've used before, and that is tcdf. Since we're looking at a t-test statistic, we know that we're going to need the lower limit, we're going to need the upper limit, and then we're going to need the degrees of freedom. Okay, so we have tcdf. The lower limit is 1.41. We can use the upper limit of 9999. Okay, now, the degrees of freedom in this scenario isn't going to give us the exact p-value if we use 8 minus 1, which is 7. Okay, because we have more than one particular population. So what we're going to have to do is we're going to need some more information here. So a word about degrees of freedom. So if I want to be able to find the exact p-value, I'm going to have to do a little bit more work by hand. So a word about degrees of freedom. Okay, the degrees of freedom used to determine the p-value presented in the by-hand solution of example 1 are conservative. This means we would require more evidence against a statement in the null hypothesis than if we use the formula for degrees of freedom given below. So results that are more accurate can be obtained using the following formula for degrees of freedom. So the degrees of freedom in this case that we wanted to put into this calculator, we would have to do the following calculation. Okay, so we're going to have to take the standard deviation squared divided by population 1 plus standard deviation of population 2 squared divided by population 2, and then square that. That's what's in the numerator. And then we need to divide it by the denominator. So we're going to take standard deviation squared divided by population 1 squared over population 1 minus 1 plus standard deviation of population 2 squared over population 2 squared divided by the sample size of population 2 minus 1. So if you can follow here, this is what I did. So let's just go ahead and review this information. So what we're going to do is let's just take a look at this numerator. So we have the following. So we're going to have parentheses and then second parentheses. Okay. Let's see here. Okay, what we can do for the following is, let's go ahead and take a look at this order of operations. So we're going to work inside the parentheses. So we're going to take parentheses 3.584, just so that we don't miss anything up. We're going to square that and then divide that by 8. That's going to give us this first part. And then we're going to add that part. So we're going to add plus parentheses 3.418, square that, and then divide that by 8. Okay, now that we've added those together, now all we need to do is take the square of that answer. And so therefore that gives us 9.400187371. So that's going to be in our numerator. Okay, when we try to do this all at once, we can miss parentheses, so it just makes it a little bit easier if we do it this way. Now we're going to look at the denominator. Okay, so let's take a look at this first term here. So in the numerator, we have parenthesis and then parenthesis 3.584, and then we're going to square that. Okay, and then we're going to divide that by 8. Okay, and then what we're going to do is we're going to square that, because that's what's written in the numerator. And then we're going to divide it by 8 minus 1, which is 7. Now we're going to select plus. Now we're going to take, okay, parenthesis, and then parenthesis again, 3.418. We're going to square that. We're going to divide that by 8. And then we're going to square that again. And then we're going to divide that by 8 minus 1, which is 7. And you can see here it gives us 0.6729497851. So on a calculator, I'm going to go up here, and I'm going to hit enter. And then I'm going to divide this by this answer here. So I'm going to hit second answer, which is this one here. And then what that does is it gives us the following value. It gives us 3.9686. Okay, so that gives us the degrees of freedom. All right, so the degrees of freedom is 13.9686321. Now, when using this formula to compute degrees of freedom, you round down to the nearest integer to use the table. Okay, in this case here, for hand reference, it is recommended that you use the smaller of the degrees of freedom. But in this case here, we're going to round down, in this case, to 13. So we're going to use the degrees of freedom to be 13.96. So let's go ahead and use the degrees of freedom from what we got over here to be 13.96. So we're going to put that in here and then calculate that in our calculator to give us the p-value. So coming back into our calculator, okay, we got second distribution, scroll down to TCDF. We know that our lower limit is 1.41. We know our upper limit is 9999. And then our degrees of freedom is 13.96. And then we're going to select paste. And then select enter. And then we're going to see what our p-value is going to be. So here's our p-value. Now, if we round that to 3 decimal places, then we get 0.090 for our p-value. Okay, now the next step is we want to be able to compare the p-value with the significance level. Okay, so what does that tell us? Well, that tells us the null hypothesis is rejected if the p-value is less than alpha. So let's take a look at the p-value that we found and then compare it to alpha. Okay, so the p-value is p-value, go ahead and rewrite that. So it's 0.090. And our significant level was 0.05. Okay, so what do we know? We know that this is greater than. So since it's greater than, we do not reject the null. So now we need to write our conclusion. So what does our conclusion tell us? Well, we would then say that there is not significant evidence at the alpha equals 0.05 level of significance to conclude that carpeted rooms have more bacteria than uncarpeted rooms.